are the symbols that are used, what is the property, and what values it could take. So the spin can take on values plus half and minus half. For the two states, 0 and 1, you can see the others, the orientation, the shape, and what all values it could take. Now, coming to qubit. This is the base foundational unit of a quantum computer with which operations will be performed. You have to manipulate the qubit just like how we did with bits 0 and 1 in the next qubit. This is the basic unit of information in quantum computing. It can take on values 0 and 1. The beauty is that it's not only 0 and 1, but it can take multiple states simultaneously, which we also call it a superposition of 0 and 1. In the further slides, I'll explain to you about the Bloch sphere, the three-dimensional one, and how every point on that sphere can be of some combination of the probabilities of the 0 and 1. I can have 10% 0, 90% 1, or 20% 0 and 80% 1. That combination of the probabilities of the values that it takes can put that point anywhere in that sphere. So I'll explain that to you. So the major difference is that the classical bit can take on only two values, that is binary 0 and 1, whereas the quantum bit can take on values 0, 1, and simultaneously it can be many other states, but only until it is measured. The moment it is measured, it will lose that superposition value. And we come back to the classical state of 0 and 1. In the following slide, I will explain that also to you. Now this is represented by a single atom in one of the two states denoted by 0 and 1. So you can see because it takes that light pulse when it is there, it will take the energy and jump to the excited state. So ground state represents 0 and the excited state represents 1. So this is by a process called photoexcitation. So light or the photons hits the electron, gives it enough energy to jump from lower energy level to a higher energy level within the atom. As I said, spin up and spin states are extremely important to understand the working of the qubit. The two possible states of the qubit can be represented using spin up and spin down states. Spin up represents state 0 and spin down represents state 1. These are used to encode the information in the quantum computers. And if you say spin up is plus half and spin down is minus, as we have seen. Now, another very important term is the Schrodinger's wave equation. Now, this exactly gives you a mathematical framework or a mathematical representation of how the qubit is represented. So, Erwin Schrödinger first introduced the wave equation in 1926. This equation could be used to predict the position and the behavior of the quantum particles. It describes how quantum state evolves, the quantum state of the system evolves with time. So that means the time also has a factor to play. Wave function is a mathematical description of the quantum state of isolated quantum system. Now look at this. What does that wave function actually express? All the possible outcomes and the probability of each outcome. I said all the possible outcomes means, and for example, I have a single qubit. I can have 0 and a 1. And I can have a probability 50% 0, 50% 1. Or a 25% 0 and a 75% 1. So this wave function will denote that. So this describes the quantum state and of the qubit and how the information is encoded. We represent it in a certain form, that is psi is equal to alpha, and we have ket 0, K-E-T, ket 0. You have a vertical line, a 0 with a greater than symbol. That indicates the quantum bit and not a classical bit. So that's called a ket 0 and a ket 1. Okay, so psi is equal to alpha square is the probability of it being 0. Beta square is the probability of it being 1. It is a superposition. So which means it's a combination of those alpha and beta complex numbers representing probability amplitudes of state 0 and 1. So this will satisfy the normalization condition because we all know every probability has to sum up to 1. We all know that every probability has to sum up to 1. So this ensures that the total probability of finding the qubit in the either state is. Now, this is very important for us to understand. If it's too much, just don't worry. I'll just tell you very simple. So, generally, the visual representation of our qubit is in the form of a log scale. So, it's a geometrical representation of the pure state space. So, what you can see here or what you can understand is the north pole. You have all the three axes, right? X, Y, and Z. So when it is 0, 0, and 1 and 0, 0, 1, that will represent state 0. And the south pole 0, 0, -1, 0, 0, -1 will represent the state 1. And you have theta and phi, the two angles, which is denoted there. But theta moves from 0 to pi only. You all know pi is 180 degrees, right? And phi will go from 0 to 2 pi. So 2 pi will be 360 degrees full round. So you can see that in that. Okay. So 0 plus get 0 plus get 1 divided by root 2, that forms the superposition. Okay. It's a value which is the superposition. You can also represent them in Cartesian coordinates as x is equal to sine theta cos phi, or y is equal to sine theta sine phi, and z is equal to cos theta. So basically, it's a representation mathematically for you to understand or visualize how so the IBM composer, if you go and log in and then you check the qubit, it will show you in this form. It will show you and you can study that, you can make variations and study. Now, let's come to the very important, the superposition, entanglement. These are terms that are very much used in designing our quantum algorithms. So the quantum algorithms can execute when the quantum circuits are generated. So for the quantum circuits to be generated, the quantum gates have to work. Okay, but the quantum gates are designed taking these quantum mechanics principles. And one of the most important one, superposition. It means a quantum particle can exist in multiple states simultaneously until it is observed or measured. Now, I'm giving you two examples. One in the form of an electron, so that the electronics people can understand electrical electronics, even from the computer science point of view, or in general, you can see that. So an electron can be in multiple positions around an atom at the same time. For a light pulse to affect the qubit, frequency of the light must match the energy difference between the two states of the qubit, that is 0 and 1. Now that is called resonance. And when light pulse has the right frequency, the qubits will absorb energy and they change the state. The previous diagram when we saw 0 change to 1, you didn't see it like that. You saw that from the inner orbit, there are jet jump to the outer orbits. But here you can see that they are connected there. Why it's shown like that is because we can't still determine whether it's in 0 or whether it is 1. It could be in multiple states. Simultaneously 0 and 1. I said different percentages of the probabilities. The likelihood of it being either here or there, and hence it is shown like that. Yeah. So, in simple terms, when a light pulse interacts with the qubit, it can make the qubit jump from one state to another, depending on the energy the light emits. Now, the second example. You're going to flip a coin. What is it? Is it heads or tails? As it is spinning and spinning and spinning, while it is spinning, are you sure whether it is going to land in on heads or tails? We are not sure about it. It is similar to that concept only. Only when it drops, then we can make out whether it is head or tail. Same way here. As long as in the quantum state is measured, it is in a superposition. Only when it is measured, you get to know what exactly it is. It will collapse to either 0 or. So, flip a coin, heads or tails. Once we see how the spinning coin lands, we can be sure of it. But while the coin is still spinning in the air, it's neither heads nor tails. It's some probability of both. And see that a coin, when it's spinning, no, it need not be always vertical. Sometimes it will be at 30 degrees angle or at 60 degrees angle, at 45 degrees angle, and so on. Depending on what is the angle from 0 to 90 degrees, the probabilities of 0 and 1 change. Depending on the coin, when it's spinning, at what angle it is spinning. Depending on that, the probability changes. So quantum coil is the superposition of heads and tails at the same time while it's spinning. When it lands, it's either heads or tails as shown picture. Now, I think you can get a better idea looking at this. We're combining the direct notation. It's called Dirac notation, D-I-R-A-C. The Schrodinger wave equation, Dirac notation, plus with the help of quantum. So you can see here, this alpha, the probability of it is being in um, heads, probability of it being tail, it is the superposition of it. So you can see the coin has not fallen down. It's a superposition. So this is the superposition concept. So it's a two-level quantum mechanical system, unit of information used in quantum computing, as you can see this. Right? Now, we also have to know how it's represented mathematically. We need to represent it mathematically. We can have vector or matrix notation. So look at this alpha, the zero when you see it is 1, 0. The one which is lower is what it signifies. In beta, it is 0 and 1. So that is the 1. And then psi is alpha or beta. So you can see this. The probability, as I said, alpha squared, beta squared, that alpha squared plus beta squared is equal to 1, all the way to infinity. Now, to get better idea of this probability amplitude, so when the qubit is measured, it collapses to one of the basis states. So only 0 or only 1 is called a basis state. Whereas if it's in a superposition of 0 and 1, it is called a space state because it's in space. So if it is either 0 or 1, it's a basis state. So when it is in superposition, it will be the space states. Only when it is measured, it will collapse and get to the basis state. So equal probability amplitudes. Now when it is 50% this and 50% this, you can write it as 0 plus 1 divided by root 2. So 1 by root 2 whole squared plus 1 by root 2 whole squared, that becomes a half. The probability of measuring the qubit is any disturbances there are it's not able to hear. So we are able to hear. Then I think that's good enough. No, my mic is not hearing. It's a small audience only. I think so. Yes. Shall we continue without the mic? YouTube streaming only packets. Please, shall I continue? Yes, yes, no. So is this clear how it's represented? One second. Thanks. Meanwhile, anyway, you can go to your slide. Any questions? So actually, when I said balance of population, both 0 50% likelihood, 1 50% likelihood. This is used in quantum algorithms because it represents a qubit that has equal probabilities of collapsing to either state. Now, for you to understand it clearly, I ensure that I write it for one qubit, two qubits, and three qubits. So you can extend for any number of qubits. So if you see the chart, how it is written for the one qubit, 1 by root 2, 0 plus 1. Because in the previous slide, we saw how that half and half comes here. Okay. So half, alpha squared half, beta squared half, both are added, that becomes the 1. So 1 by square root 2 whole square. That's how we derive it. So likewise, for a 2-bit, classical we can have 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. Same way that is there. But 4 combinations, so 1 by root 4 square plus 1 by root 4 squared plus 1 by root 4 squared plus 1 by root 4 squared 4 times. That is the same as half. That's why I've written, if you ask me why, 1 by root 4 is a half. That's why it's written as a half. Now look at 3-bit. So 3-bit means we have 8 combinations, 0, 0, 0, 0, 0, 1 and so on up to 1, 1, 1, 1. But 8 combinations, so 1 by root 8, 1 by root 8, you have to keep on adding. Then you can write the Schrodinger wave equation shell. This is how the qubit can be represented. Now, as I said, from superposition, for it to collapse to a measurable form, you need to do the measurement. So quantum systems exist in a state of superposition until observed. So quantum measurement is the process of observing or measuring quantum system, such as a particle or an atom. Look at this now. As you only look at the diagram, I'll just explain to you so you'll understand. If the spin points to the left as it is now, particle goes to the left detector. If the spin points to the right, particle goes to the right detector. Are you able to observe that? If the spin points upward, the particle is a special quantum state where it can go left and right at the same time. Like it's in two places at once. That's superposition. But when the detector finally registers the particle, it will show up on any one side, either left or right. But in this case, it was left. But there is a 50% chance that it can also go to the right. So is that diagram clear? Right. Now, a very, very important thought experiment. You know that you go to the lab and do experiments, but in quantum computing, we have a number of thought experiments for us to analyze and understand various concepts. And the new quantum computers that have been in the market now, they are based on the Schrodinger's cat thought experiment only. So I thought it was important to add it here. It's a very interesting one. So the setup is inside the sealed box. We have a cat, a radioactive atom with a 50% chance of decaying, a Geiger counter to detect if at all the atom decays, and a vial of poison connected to a hammer ready to break if triggered. Now, how that hammer is going to be triggered? When the atom decays. Okay, and there's a 50% that the decay will happen, but we don't know when the decay will happen. Okay, so if the radioactive atom does not decay, the cat will be alive. But if the atom decays, the Geiger counter it will be triggered by that vial of poison that is broken when the hammer hits it. So it will detect it, triggering the hammer to break the vial and release the poison. And when the poison is released and it is in a sealed box, will the cat be alive? No, it's going to be dead. Now, what is this experiment showing us? It is depicting how superposition works. So, before we open the box, sealed box, and see, we are not sure whether the cat is dead or alive. It could be dead, it could be alive. If there's a 20% chance that it will be alive, 80% chance that it will be dead, or 80% chance that it will be alive or dead, whatever it could be. We are not sure until we open the box. That means when an observer opening the box and observing, that's the measurement time. Until then, it is in superposition. Only later, when you open and see, then it stops being in a superposition condition. It is that you will find the cat either dead or alive, any one of them, one of the states found. So the big reveal is when we finally open the box, we observe that the system of the superposition collapses. At that moment, the cat becomes either alive or dead, but not both. So this shows at the quantum level how things can exist in multiple states until we observe them. It's a very good way of understanding that. Otherwise, you're always puzzled about that behavior of it existing in multiple states simultaneously. Even I took some time to understand that concept. So next important one is interference. That's also very important. It occurs when the quantum particle can take multiple paths at the same time and different paths interact with each other. But then the way the waves add or go in negative direction, either it can add or it can reduce, right? So waves of matter can interfere constructively or destructively, leading to the formation of interference patterns. So interference occurs when quantum states overlap, producing regions of enhancement, that is constructive interference, or cancellation, that is destructive interference, and that we can see on the right side. how the uh, thing adds or amplitude gets deducted. Now, how this can be shown? A very, very important experiment is our double slit experiment. So, as you can see, the experimental setup, there's an electron beam, the generating gun. So, the electrons pass through a frame where there is a double slit. There are two slits, and you can see that there is a screen behind. So the electron passes. You are not sure which electron is passing through the first slit, which electron is passing through the slit, all that you don't know. But you know that on the screen it forms an interference pattern. That is simply a light and dark bands. It just forms a combination of light and dark bands. So individual photons are directed towards a barrier with two slits. Beyond barrier, there's a screen. An interference pattern of bright and dark bands emerges, even though each electron passes through one slit at a time. So again, here constructive and destructive interference happens. So this shows wave-like behavior of particles. And you can see that this experiment exhibits wave-particle duality because when it is measured, then it's a particle. Otherwise, until then, it is waves. They act as particles when detected. But while they are traveling, they act as waves. And if you see in experimentation, writing in the program and board or seeing an IBM composer, you will see the outputs like this. So you have here, there are detectors placed near the slits to observe which slit the electron goes through. The interference pattern disappears and simply you will have only two bright bands appearing. Okay. So active measurement collapses wave-like behavior into particle-like behavior. Another very, very important one for quantum communication, quantum internet, quantum teleportation and all is the entanglement. This entanglement is also an important concept. It's a phenomenon where two or more particles become so interconnected that the state of one particle instantly influences the state of the other, regardless of how distant they are, how remote they are. One can be in one universe, the other can be in another universe, but still there will be some kind of connection. It's a not physical connection. Okay. So this crucial resource for quantum computing and communication. It's just like you have a magical connection across the universe. You can think of a pair of gloves. You and your friend have a pair of gloves. One will be the right hand glove, one will be the left hand glove. So if one takes this and that friend goes to some other country or some other land, and yet when you have this one, you know that the other person has the other glove. So it's just like, and then when two particles like photons or electrons become entangled, their properties are mysteriously linked. So if you measure one particle, the other moves instantly and takes on the corresponding property, even if they are light years apart. So we'll see that example, especially the most important example for entanglement here is the creation of Bell states. And we have to create a Bell state circuit in order to execute certain things. So let me tell you what this is. One of the most well-known examples of an entangled state is the Bell state. In the state, neither qubit has a definite state on its own. Always it is influenced by the other. Entanglement. So there is some effect of one on the other. They cannot be independent. They are correlated in such a way that if one qubit is measured and found to be in state 0, the other will be in state 1 and vice versa. They are fundamental in, as I said, quantum computing and quantum information theory. They are building blocks for many algorithms. So that's why it's important. Mainly quantum teleportation, that's one protocol that is being used, where you can transmit quantum information between two different locations. Teleportation, the word itself tells what it is. And then super dense coding. So when you do information coding, you can handle more number of data, less time. Then quantum cryptography, of course, you all know cryptography is for security, data security, network security, whatever. So you encrypt and decrypt, you have used so many mathematical formulae, frameworks, everything, isn't it? Now, how it's represented here, you can see that block sphere, okay? And you can see that plus and minus are simply symmetric and asymmetric. So you have only that 0 and 1, 2 bits or 4 bits. Sorry, 1 bit and 2 bits. With the 2 bits, you have the 4 combinations, right? And that shy plus and minus, again 5 plus and minus. So this is how the well states are. And then we have very important concept coherence and decoherence. We all know coherence means in synchronization with. Decoherence means not in sync. When you're in sync, we say coherence. When you're not in sync, not coherent. So coherence is tiny particles or waves in a quantum system. They stay in step with each other, means they are together, sync with together, maintaining a steady relationship. So this allows interference, superposition, entanglement, which are very important for quantum computation. Coherence can also be disrupted. How? By heat, random movements of particles, okay, electromagnetic interference, so signals from nearby devices, imperfection in the quantum gates when they are so, tiny error system used to control quantum particles. So that is the reason why quantum computers are all placed in vacuum or very, very cryogenic temperatures, low temperatures, in order to avoid the environmental interference. Once the environmental interference comes in, the quantum computers lose their superposition, they collapse to the classical type. Okay, that is the reason. Decoherence is the process where quantum system loses coherence due to interactions. So it leads to system behaving more like a classical object. And it's a challenge because for us to create stable quantum computers, all this while it was that noisy, NISQ, noisy with a lot of error rates, quantum computers. Now they are working, research is going on in order to reduce errors, error corrections, right? So, to reduce decoherence, they have to be kept in sub-zero temperatures or in vacuum so that they can avoid any interference. Decoherence can be used to create ultra-sensitive sensors. When you need it to be very, very sensitive, then also it's important, right? Now you can understand that in terms of basis quantum state 0 and 1, and if it is coherent, how it is, and if it is incoherent, how it is. The um, diagram here is self-explanatory. Now, we completed the quantum mechanics principles, the foundational principles. Quickly, we'll just compare classical versus quantum. So, this itself will show you everything. If you have a 0 or a 1, you can only have one out of the 2 raised to n possible combinations. Like we have 2 bits, for example. If we have 2 bits, then we have only 4 combinations, 2 raised to n, 4 combinations. So, only one of them you can pick, 1 out of 4, right? But in quantum, you can have all of those simultaneously. It could either be in 0, 0 position with a probability that 1 by root 4, 0, 1 with 1 by root 4, or 1, 0 with 1 by root 4, and that way, isn't it? So, you have all of origin. So, imagine the problem solution space. It increases tremendously, and hence you can handle uh, the solution for very complex problems that handle huge amounts of data. It's only because of this. Okay. And then we all know in a classical computer, we have binary system, logic gates, integrated circuits, von Neumann architecture, stored program concept, computer unit, arithmetic logic unit. All of us have studied input output system, the buses, fetch code, execute cycle, all these things we have seen. But in quantum computers, we make use of mainly superposition, entanglement, and interference, and qubits instead of bits. So you can see that here, basic unit of information 0 and 1, here 0, 1 and superposition of both. Information representation, it can exist only in one state, but this can exist in multiple states. Here, data processing is sequential or parallel, with only fixed number of operations per unit time, but here it can process vast number of possibilities that I have shown you. Error rate and correction, in classical it is low error rate, well established low error correction methods are already developed since long we have. But whereas in quantum computing, higher susceptibility to errors due to decoherence and noise, but research is going on to eliminate as much as possible the errors and bring in a better working quantum computer. Hardware and architecture, we know for classical computers, it's using transistors, classical logic gates, And then they are based on silicon technology. We all know that. But quantum computers use quantum gates. Then qubits are implemented using, as I said, the to generate the QPU, the quantum processing unit. Different technologies like superconducting circuits, trapped ions, photons, and topological qubits. They all can be used. And logic gates, AND or not, NAND or and all, that. Here in quantum, we have Hadamard gate, which is very important to create superposition, poly X, poly Y, poly Z, then control gates. And again, you have single qubit gates, multiple qubit, that is two qubit gates, and so on. Algorithms, always in classical, they are deterministic algorithms, whereas in quantum, they are always probabilistic algorithms. You've seen, no, they are a certain probability. So they are probabilistic algorithms. And classical it is sorting, searching, the search algorithms and so on. In this, we have Grover search, Shor's algorithm, factoring, quantum phase estimation, and many more. Then scalability, this scales linearly with the number of bits in classical, whereas here exponential, I told you in the beginning itself, exponential speed up. So it scales exponentially and not linearly. Applications for a wide range of everyday applications from arithmetic to complex simulations, what we are using currently. But this is especially for cryptography, optimization, simulations, and complex problems. And speed, the same thing in a reverse way to store. Okay, so that is about the classical versus quantum computing. So we can appreciate what is this paradigm, what is this paradigm. Now, coming to the basic structure of the quantum computer, many times only some portions will be dealt with. We need to have an integrated view of what a quantum computer system has. So, some things I have already explained, which I will go quickly. What is not explained, I will go further. So, basically, qubits, which are the fundamental units of quantum information, then quantum gates that manipulate the states of the qubits. So, why we use these quantum gates? You can perform operations like creating superposition. First, you have to create the superposition. Then you can flip the state of the qubit from 0 to 1 or 1 to 0. So you have some quantum gate for flipping the state of the qubit. Then introducing a phase shift. I told that theta, pi, and all that you can introduce phase shifts. Then you can create entanglement. I told entanglement is also important in certain protocols, especially in quantum communication. And exchanging the states of the qubit. Swap. We have a gate called swap gate. So it will swap or exchange the state of the qubits and many more. Okay, few I have just listed because in 1.5 hours I will not be able to cover. There's so much to do. Then we have quantum circuits. The sequence of quantum gates that are applied to the qubits to perform the computation. So you create a circuit. So that circuit you can create with the qubits, with the wires, with the measurement device, and a classical register also, because when it collapses, you need to measure and keep it somewhere. No? So you need to have a classical register also. Okay. So then quantum processor, it's also known as quantum processing unit, QPU. We all know CPU, central processing unit. We all know GPU, graphical processor unit, processing unit. Now this is quantum processing unit, QPU. This performs quantum computations, just like our CPU performs classical computations. Then quantum control systems, very, very important because this implements the quantum gate, just like we had control unit in our classical computer. Control systems are very important. Actually, they generate certain signals to coordinate all the activities. They implement the quantum gates, guide the behavior of the quantum systems. It's a control. And we have quantum physical systems, mainly the dilution refrigerator to keep the system cool, so that to avoid any environmental interactions and trying to again have interference and bring it to the classical state, to avoid bringing it to the classical state. So quantum gates, I just told everything. One thing is in quantum, it is reversible. In classical, it is not. If I have logic gate, I give inputs, no. In classical gate, after I apply AND or what output I get, I can't bring it to the input state. It is non-reversible. Whereas in quantum, it's reversible because it collapses to the classical state. So it is reversible. Then there are so many quantum gates here. Okay. It just gives you a brief summary because we don't have enough time. And Hadamard gate most important to create superposition, poly X, Y, Z, phase flip or bit flip plus phase flip, bit flip. So I've given the purpose also. Then identity, which keeps it the same way, phase, so adds a phase, and then C naught, control, conditional not gate. C naught is another very important gate. Toffoli gate, controlled C naught, and swap, I said, swapping the states of the two bits. And then controlled unitary. This U is very, very important. Unitary transformations are performed with a unitary gate. So I'll tell you. So uh, then we have quantum circuits. Quantum circuit is used to implement quantum algorithms. We all know logic circuits. If we design the logic circuit, then a logical operation will perform decoder, encoder, whatever. We do that, isn't it? Full adder, half adder, everything. Like that here. It consists of qubits and quantum gates which manipulate the state of the qubits to perform computations. So again, in quantum circuits, you can't have a complete circuit without the qubit. You start from the qubit, either the zero condition or one condition or whatever. So you have to have the gates, Hadamard gate or swap gate or C naught gate, you have to put it. Then you have to measure because without measuring, you cannot get your output, right? It will be in some status. Then classical research store the results of the quantum measurements, and this could also be used for hybrid quantum classical algorithms. You get a good idea when you go and look at IBM Composer. You don't have to do anything. Everything is there. You have a tutorial. You just go and look. You'll understand these things much better. So as I said, your single qubit gates, multi-qubit gates, entanglement and measurement. These four are very, very important for quantum circuits to be designed and operated. Now, one example I said, we talked about the Bell states, right? Four Bell states, isn't it? That we can create. How to create? Very simple. You can have the circuit design. I said Q of 0, Q of 1 are the two qubits. Put a Hadamard gate to create the superposition and then the controlled NOT gate. And then you get it's entangled and the Bell state is created. So you can see this Bell state will be created. That's all. If you see the measurement, the output here, you will get this. Right? Like this, we can generate. I only showed you simple one. You can do more complex operations based on what you want. Explore an IBM Composer. It's a simulator. Okay, you don't have to do any coding or anything. It's a simulator, but it helps you understand all these uh, concepts very nicely because that simulation you can change things and all and keep on studying. Right? Now, quantum processing unit, specialized hardware device designed to perform quantum computations. QP is where qubits are housed and quantum gates are applied. Requires extremely low temperatures to maintain quantum coherence. Physical systems, as I told you, it's cooled with dilution refrigerators. It should be in ultra high temperatures, typically in millikelvin range. And control systems, as I said, it will send precise signals, microwaves, lasers, magnetic fields to manipulate the qubits and implement quantum gates and guide behavior of quantum systems. They are critical for quantum computing, quantum communication, quantum sensing, and so on. So, to achieve specific quantum gates, perform desired quantum operations, maintain coherence in the presence of noise and decoherence. So it's important for the control system. Now, as I said, the types of quantum computers that you have, it depends on what is the leading quantum processing unit technology that is adopted. Now, what is popular is superconducting. Okay. So superconducting qubits, trapped ions, photonic qubits, and topological qubits. Now, we'll discuss that a little in detail later in the types. But for now, as with respect to the quantum processing unit, it can be designed with any of these. And basic structure of the quantum computer, when I say it's not about only the cooling system, the control and the measurement system, the quantum processing unit, but as I said, when you measure, you need to have classical registers. So the classical processing layer is also important. And of course, the application layer where we enter. So in the application layer, we can use Python and Qiskit programming. So you can use even the web-based ones. Okay, you need not have Jupyter Notebook only. You can do Google Colab also. In Google Colab also, you can write Qiskit programming. So quantum programming frameworks we use. And then, as I said, classical processing layer for the pre and post processing task. I'll tell you why. Because we cannot access quantum computers directly. Through our classical only we are accessing, right? So there are some pre-tasks to be done. Likewise, when the output comes, we are not accessing the quantum computer directly. We need to do some post-processing tasks and then we get our result. So that's there in the classical processing layer. The rest three I've already explained to you. So I know quantum hardware has four abstract layers: quantum data plane, control and measurement plane, control processor plane, and host processor plane. Host processor is where we give the job. We do it on our system. Quantum software will implement the quantum algorithms. So you can see in this quantum data plane, I've given all the features there. Heart of the quantum data plane is the heart of the quantum computer. Qubits reside here. It includes physical qubits and structures needed to hold them in place and support circuitry needed to measure the state of the qubit, whether it is a zero or whether it is a one, and so on. Now, control and measurement plane responsible for carrying out operations and measurements and converts control process digital signals, which indicates what quantum operations are to be performed, to the analog control signals needed to perform operations on the qubits in the quantum data plane. Because we need to transfer from our classical computer to the quantum computer and submit the job there. After it is done, we have to get it back. That's why these interfacing layers will be there. Okay. So converts analog output of measurements of qubits to data plane to classical binary data that the control processor can handle. So control processor, it has its own thing, quantum error correction, all that has to be done, right? And then host processor, it will handle network, storage, user interfaces, and so on. So software development tools that are necessary, they will run on the host processor. Qiskit programming, all that is on our computer. That is the host computer. As I said, Qiskit is IBM's one. CIRQ, you can work on that also. That is a Google developed open source framework. They are all open source. Forest, then quantum development kit, all these are open source. You can start your research on quantum computing using any of these. Then the work to this will give you a better idea of how it's going to work. First of all, the problem is defined. You write a quantum algorithm to execute that problem. Then it can't simply just execute in our classical computer and give us the output. It cannot be like that. Okay, in the memory. For that particular quantum algorithm, the corresponding quantum circuit has to be generated. Okay. Once the corresponding quantum circuit is generated, like how it looks here with the Hadamard gate, with the unitary transformation and so on, that combination will depend on how this algorithm is built, and depending on those functions, those will be invoked to generate that circuit. So you get the visual representation. You have many in the packages. When you do the Qiskit programming, you get the visual representation of the circuit. Now this will go to the compiler, quantum compiler. So after it is compiled and it is ready for execution, it can be executed in two scenarios. One is on a quantum processor directly. Another is on a quantum simulator. So far, whatever we've been doing is on the quantum simulator because we didn't have a quantum computer. Commercially, they are just coming now. But some quantum computers are there, IBM, somebody has they use. So for us, through cloud, they allow us to access or deploy our thing here. Yes, previous. Sorry, sir. Yeah, sir. So you can have it on the quantum processor or quantum simulator. And look at this. If you see this, you get an idea. My computer, you JSON file, okay? JavaScript object notation goes to the quantum cloud service. The job is submitted to the QPU, the quantum processor. The result comes back to the cloud and then it comes back on. I think now it's clear how the quantum programs will get executed, right? Any doubt about this? Yeah. Now, generally AWS and all, we have a service. So service that runs hybrid programs generates quantum circuits from my computer. Then it goes there, generates our quantum circuit. So you have the control server, the qubit to access it. Now, as I told you, using those four technologies, we have different types of computers. Superconducting quantum computers, I have just put pictures of how they look, each one of them. Superconducting quantum computers, ion trap quantum computers, photonic quantum computers, and topological quantum computers. So I tried to put everything just in one slide, these four types. You can see the IBM Q quantum computers picture, and you can see Google Sycamore quantum computer. They have the superconducting material as a representation of the qubit. Most widely used, operates at cryogenic temperatures, and minimizes noise and decoherence. Superconducting materials are cooled to very low temperatures to create the circuits. Now, those qubits are named as transmon qubits and flux qubits. And this is used by IBM, Google, and Rigetti. Okay. Now we have ion trap quantum computers. They use ions, which are charged atoms, as qubits. So the way in what technology is used in generated qubits, depending on the types. They use electromagnetic fields to trap and manipulate ions using lasers to perform the quantum operation. So you can see that the beam of laser there on that, the ions are trapped there. And you can see the zero state and the one state, how it is excited and grounded state. They are more stable than other types of quantum computers. They can perform more complex calculations. The physical qubits are trapped ions. They are confined to a magnetic field and manipulated using laser. Now, examples are ytterbium ions and calcium ions. Advantages, long coherence times and relatively easy to control individual qubits. Challenges, of course, scaling up to large number of qubits is complex at this point of time. Research is going on. They will definitely improve later. It's a challenge only at this point of time. Slower gate operations compared to superconducting qubits. Now used by Honeywell and IonQ. This is the Honeywell diagram. Then we have photonic quantum computers. So light pulses are used. So you have vertical polarization that indicates a zero and a horizontal polarization that indicates one. So for photons used as qubits, they use lasers and other optical components like beam splitters, phase shifters, and so on. They are they are faster than other quantum computers. For example, even you must have heard a lot about quantum dots. It's a very, very important term when you keyword when you search quantum, it will come up quantum dots. These are also called artificial atoms, which is shown there in the last. So nanoscale semiconductor particle that exhibits unique quantum mechanical properties. What advantages? Room temperature operation, potential for integration. Why room temperature? Light only, no photons. Then potential for integration with existing fiber optic communication infrastructure and long coherence times. It has to have coherence for a longer time. That's an advantage. What are the challenges? Difficulty in creating deterministic photon sources and scalable photonic circuits interfacing with other quantum systems. And this is used by Xanadu. You can see that below here, Xanadu and Psi-quantum companies. And the last type, topological quantum computers. Quantum information is encoded in the braiding of exotic particles called anions, A-N-Y-O-N-S. As they have ability to store and manipulate information more stable than the others, it makes the computation fault tolerant. That's also important for us, right? That means error detection and correction, they are better. So this gives more fault tolerance. Example, Majorana zero modes. They are still in the early stages of development and this is being used by Microsoft. So how this works, you can see actually there is a parallel that is drawn between computation and physics. Can you see that in that diagram there? There's a parallel drawn between computation and physics. The initial state of the quantum computer corresponds to configuration of the ions. Then qubits are encoded in the corrective state of the ions, represented by braiding patterns or fusion operations. Then logical operations are performed by physically moving the anions around each other in certain braiding patterns. Okay? And to read out the quantum state, the anions are combined or fused. The result of the fusion determines the output of the computation. Again, that was depending on the technology that was used for the QPU. Okay, but this is based on how it works. So, quantum annealing, analog quantum simulations, and universal quantum computing. I try to put them all just here. So you can see these are the three different types of quantum computers. Again, based on their purpose, based on the purpose and how they operate. This is used to find global minimum of given objective function. So for mainly for optimization, it is used. Least powerful, most restrictive, easy to build, has few qubits, and can perform only one specific function. It's mainly used for optimization purposes. The first one, quantum annealing. And you must have heard about that term also, quantum annihilator. It's a very, very common term that's used. Then analog quantum simulations are the general one. NISQ, you must have heard about it. Noisy intermediate scale quantum computer. NISQ, noisy intermediate scale quantum computer. Uses continuous variables like position and momentum to represent and manipulate information, operates on quantum states and employs continuous transformations. It has about 50 to 100 qubits. The computational power is high and is used for simulations, majorly in chemistry and material science. Majorly in chemistry and material science. Then universal quantum computing poses a number of technical challenges, most powerful, most general, hard to build, exponentially faster, than 100,000 physical qubits. Computational power is ultra high. High is the previous one, this is ultra high. Used for secure computing, machine learning, cryptography, etc. So here again, many more points are there. Like D-Wave is one company, IBM Q, Google Sycamore, IBM Rigetti. So whatever I have told there, it's almost the same. Let's move. This also just one slide I just told you because I can't get into more of algorithms. You know why we need the quantum algorithms? Exponential speed up, quadratic speed up for search problems, efficient simulation of quantum systems. You can solve optimization problems, then revolutionary cryptography and advancements in machine learning. So some of the well-known algorithms that we need to first study in quantum computing, which will further be used for other algorithms and so on. Our Dewey-Josha algorithm, that's the first one which just gave the advantage of quantum computing over classical through this algorithm. So it's very important. The fundamental algorithm determines if a given function is constant or balanced using fewer queries than the classical computers. That's why it finds importance. Complexity analysis, understanding quantum advantage, and so on. It's used for that. Grover's algorithm search. Linear search, binary search. Many of us would have learned that, isn't it? So here it is a complex search. Unsorted database that solves the problem faster than classical. And Shor's algorithm factorizes integers, I said, and even it beats that cryptography. So they have to find other ways of doing it. Quantum Fourier transform. We all know how important Fourier transforms are. And this transforms quantum states using Fourier. See, in parallel, what we are using many things, techniques in classical computing, they're trying to get corresponding quantum algorithms for those operations also. Okay. And phase estimation, that's also an important task to be performed. And quantum key distribution, the very first protocol there, BB84 protocol. I think everyone should go and look for it. It's very, very interesting. It also makes use of light photon and how the vertical polarization and horizontal polarization explains the encryption and the decryption and how it can be found out whether there's an error or not. It's very, very interesting, BB84 protocol. So for anyone who's interested, can further go and look into it. Advantages, parallelism, we all know that speed and solving intractable problems. That is those problems that cannot be handled by classical computers. Speed, of course, I told all these fields. Limitations, decoherence, as we said, then they lose their quantum state which will again affect, right? And then error correction because they are more prone to noise and interference at this point in time. Definitely, there will be improvement in the future. Then specialized use because they can solve certain complex problems that cannot be solved by, say, for example, you take a factorial problem to find the factor of a number. You can write a programming in Qiskit programming for that also. But really, it takes more time than a classical. So we also should understand what kind of problems need to be solved using and not try and solve every problem using quantum computers. So it's not that quantum computer will replace classical computer. They will go hand in hand. They are used for very, very large amounts of data analysis and optimization and cryptography and all. But classical computing will also be there, at least in the near future. When applications, it has a number of applications, quantum sensing, quantum imaging, like we have now MRI and all those things, quantum imaging. It's again huge amounts of data. Drug discovery and healthcare, quantum machine learning algorithms are used, quantum deep learning algorithms are used in drug discovery and healthcare. Then quantum finance, as I said, portfolio, risks, everything we are using a lot of quantum algorithms, quantum simulations, and cryptography. And also, interestingly, they are using quantum computing for environment and sustainability also in the climate model. Then looking at the soils samples, study of that. So again, wherever there's large amount of data that is used, any prediction that has to be used, they are doing a lot of work at climate modeling also. These are only limited applications that I have mentioned. If you go and look at it, there are so many more applications that are that can use quantum. Then what are the research trends? I just given briefly here. If anybody is interested, you can pick up some research on quantum computing. Any advancements in the quantum hardware, that's because all these are there. I have to add this. Because computer science, I don't think they would be interested to do any kind of research in advancements in quantum hardware. But definitely, all these departments can contribute to that. Okay. Then quantum error correction and fault tolerant. Okay. That's another important area to be worked on. Quantum algorithms and applications, of course, your information science, computer science, they all can work on this more. Quantum algorithms, also quantum AI, ML, quantum cryptography, security, simulation, quantum finance, and optimization, of course. Then quantum networking and quantum internet. ENC or all that, those kind of departments can work on it. A lot has to be done on that area also. Because you have for your classical computing certain network bandwidth and all that. Our protocols will run. But when you get quantum protocols, they are a little different because the quantum concepts will be different. The mechanics concepts are huge. So the building the networking hardware as well as building the networking protocols. There has to be done. A lot of work has to be done. Then climate modeling. If no, all of us should be responsible to ensure that we now do not pollute our environment anymore and give a better environment to our next generations. So we also have to, we can work on climate modeling to suggest ways and means of improving that. So I come to the end of the session. The next decade promises to be a transformative period for quantum computing, with advancements in technology, software, and applications driving the field forward. And while significant challenges remain, benefits of quantum computing are immense, offering solutions to some of the most complex problems. Continuous research, innovation, collaboration will be essential to realize full potential of quantum computing in the coming years. And I want to say that India's national quantum mission aims to position India as a global leader in quantum technologies by developing quantum computers, quantum communication networks, and advanced quantum materials over an 8-year period, that is by 2031, with a budget of 6,003 crores. So, why I want to mention this specifically is because this much of budget is allocated. All our premier institutions, government agencies, the startup ecosystem, everyone is working towards this. As academicians, we can also contribute to the research and innovation in this field. So we can speed it up. Actually, before the National Quantum Mission, their idea was target was 2035 to get the first quantum computer, to build the first quantum computer. So now we have to split it up, 2031. So a lot of work can be done. Okay. So thank you very much. I once again thank for the organizing teams and all of you who are here, who gave a patient listening for this talk on quantum computing. Thank you so much. Any questions? I can't hear you. Can you be louder or just this too? No, no, right. Being a researcher would need to speed. But if we want to apply these concepts in economics for our students, then what will be the prerequisite and how it will be like the flow of the because it's a kind of but yeah, it's for the true. For everyone, it's a new topic. I don't think, generally, I don't believe in too many prerequisites because as and when we require something, we can delve deep into it and study. This is my opinion always. Okay, I'm always learning different things. So what I feel is it's not necessary that you should be knowing this. Of course, you should be in a position to grasp physics, mathematics, and concepts. You should be willing to try and go deeper and understand these concepts. Definitely, base is physics, mathematics, and concepts. But not that others can't do it. Definitely, anyone can do it at any point of time. Quantum teleporting is something related to psychology and physics. Metaverse, no? No, it's just a protocol because you know about this entanglement, how to transfer data from one place to another. For that, teleportation protocol is used. Thank you. Some form of realization. What do you think? One person starts thinking the same thought will start coming in some other person's mind, and that link is what is called as now internet, and that is updated Wikipedia. There's a lot of material out there, so I think if you keep exploring and exploring, being excited and passionate and exploring, we can learn a lot. Yeah. It's a very nice talk. I have two talks related to one is measurement, another is algorithms. First one is measurement. How do we know which type of measurement we have to use? No, whatever is your, I told you, the simulated environment, they have one of the component there as a measurement. But it will ensure that because now we are working on the simulated environment, you are not working directly, right? So we have to use the particular basic measurement is called what are possible states. So they have, just like qubits, just like gates, they have one measurement. That is what you could share. And how in the back end it is working, we have no idea because it is simulated. So another thing is we did create entanglement thread by using matrices. So we have C0 gate to create that entanglement. So do we have any other matrices? No, we have many. That's what I said. I put one list here. No, there are too many. You have to study in detail one by one. In the entanglement matrix. The body matrices cannot create the entanglement. Only C0 gate can create entanglement. C0 and the 3 gate qubits. Yeah, because minimum at least 2 qubits you need. No. With a single qubit, you cannot have entanglement. It's minimum at least two qubits you need to have. You even with three qubits you can have entanglement. CC naught is also there. CC naught is there. So is it any other matrices that creates entanglement? We will have to explore. What I have explored is only this. Is it how to identify whether it is maximally entangled? Now, again, for that, there is a procedure. What are the starting values of this that you put? One Hadamard gate, when you put either you started with a zero or you started with a one, and which the zero should come before or after, depending on your requirement and how it options, you need to design your project cells. I have generated all the four well states. Slight differences will be there. You need to do study and insert them and see how it is functioning there, and you will be able to understand which is the right. Because you can study that out. No, your input is there and your output will come after adding all this in the circuit. Expectation. Yes, yes. Outcome. Depending on that, you do the trial. You will get it. Thank you. Yeah. Pardon? The quantum networking in the market is also defined, if they define quantum networking, I'm not working much on it. I'm just working on the quantum algorithms. Circuit level. Yeah. Circuit level and also a few applications. Quantum ML like support vector machine, these kind of simple networking I am not covering. Only teleportation I work. So these are the that's much for quantum sensors. It's not only optic sensors. No, quantum sensors. Send lot is used and imaging. Sensors and imaging. First, I would like to thank all the participants who are present here. Now, I think everyone got the knowledge about quantum computers. Thank you very much, ma'am. I'd like to request Meher ma'am to give the token update to our resource person, Dr. Chitra Bhatis. It's a because come up. So I think what's okay, right? You take my money, it's not the day. Please come, sir. Yeah. It's very much. Yeah. These are the all of it and I don't. Still time may ask how much. Tell someone to bring. But you are it's then not stress photo. Yes. There's this now. Package comes from. Don't run up secret. Take on concept. Yeah, it's your time. Quite sense. Once parcel. It's top prices box plus company has not. You want to no. Yeshwant already have a lesson someone did. It's one take later. Yes. She should be there. You are not. What is her name? He was all three of his step. It's not so good. Tell me the one that I have from yes. Oh, then I got one. No. That's why one second. See, three modes are there. Regarding research, someone was saying, asking about how to proceed with the research. Means doing with the electrons is kit and all. It is just a plug and play. You may not be able to publish papers. Mainly, we want publishing papers. So, see where the better choice is photon based, support photon based, light based systems. We have theoretical simulation is simulation is just pure simulation is that means calculation and optimizing some parameters that you may be able to do some publishing also. So try to do that one instead of going with the community and doing the biscuit or circ and all. It will be difficult to publish. It is just plug and play type of system. So already we are remotely working. So it will be difficult for us to publish paper for the faculty. Yeah. Yeah. I think I think God was trying to divide his own last year. It's a matter of it. You should give me some students in this music. Oh, I can't say draw for like the dance music to the hands deep to the सुन गलत जाएगा सीधे